Hi, my name is Nidhi Ohri, and I'll be talking about my work this summer in the Goldberg lab group. For some background, we all know about the global reliance on natural gas, which is primarily composed of methane. Utilizing methane, such as liquefying it, is difficult, but functionalizing it is a solution to this problem and propels us towards the overall goal of transforming chemical feedstocks to valuable chemical products. Typically, functionalization of alkanes is achieved using transition metal complexes, but we've opted for a metal-free aerobic process involving oxygen as a terminal and sustainable oxidant. In our study, we opted to use cyclohexane as a model substrate for methane because it offers us experimental convenience and lets us understand the reaction mechanism. The net reaction involves the photochemical iodination of cyclohexane, or replacing one of the hydrogens on cyclohexane with an iodine atom, using chlorine anion as the photocatalyst in presence of UV light. Please refer to the reaction section for more details. My previous work led us to conclude that 1% water with respect to the solvent is an optimal condition for the reaction. With our overall understanding of the reaction, the next natural step was to scale it up, which was my work this summer. I designed a batch reactor to facilitate the slow addition of I2 reagent and conducted time course experiments with the modified iodine addition rate and modified initial conditions of the system to fine-tune selectivity towards cyclohexyl iodide and maximize the catalytic productivity over time. Please refer to the batch reactor design section to compare the results between experimental conditions, and notice on Figure 2 how the triangular data point set represents the current best conditions to achieve a good balance between selectivity and overall catalytic activity. The curiosity about flow photochemistry stemmed from the batch reactor scaling up efforts, and flow chemistry is a great way to form a targeted product in a consistent manner while obtaining data more quickly. And remember, our targeted product has always been cyclohexyl iodide. So I designed a flow reactor to facilitate the variable addition of reaction, meaning all the reaction components, not just iodine, which was the case in the batch reactor. And I conducted time course experiments with the modified reaction addition rate. Since this is a flow reactor, there was no modification of an initial state of the system. So in this case, along with wanting maximized catalytic productivity, the goal was also to observe consistency between data points as a testament to the concept of the flow design. With reference to Figure 3 in the flow reactor section, you'll notice how the first 3 experimental data sets, as indicated by the legend, do not exhibit consistency between aliquots. So to try and understand the source of this observation, I sped up the pumping rate to a relatively fast value as shown by the triangular data point set. Doing this, of course, resulted in low catalytic activity, which I anticipated, but consistency between each aliquot was observed. So why the increased speed caused consistency is still not fully understood. And so I conducted another experiment with controlled cool temperature to see if temperature affects the system. Cooling the reaction did not resolve the issue, but more tests should be done for conclusivity of data. So based on my work, we conclude that the batch reactor design with pumping of iodine reagent allows for the linear catalytic productivity of the course of experiment, and the flow reactor design has a large source of error that needs identification, but it does give faster catalytic productivity. So my next direct future work includes the optimization of the flow system and just building a better understanding of it and the parameters that it involves. And some later future work of my interest involves reintroducing metal complexes back into this reaction, specifically an iridium complex, to utilize green light and offer another way to regenerate the chlorine radical catalyst in this system.